Well, welcome back. Hope you had a good break. Um, Today I'm going to talk a little bit more about the vibrating square drum problem that I discussed the Friday before break. It's a pretty interesting thing to think about, and it illustrates a number of important facts about the wave equation. Turns out the wave equation in even dimensions is very different than the wave equation in odd dimensions. So square drums are a lot different than strings. So let me, any questions about anything before I dive into this? Yeah.
I just wanted to ask, and if you feel the answer would give away too much about exams, that's fine, but can we assume that on all exams the questions will be closely analogous to homework problems?
I tried to do that. I tried to make it, the exam questions, similar to homework problems and practice problems.
Okay, thank you.
The next exam will be a take-home exam, so maybe it'll be more like homework problems than practice problems.
Okay.
Yes.
I'm sure you'll go through the logistics more, but for the second exam, will it have? I mean, obviously anything's fair game, but will there be more emphasis between or on the chapter 3 and 4 topics on the exam? Or?
Oh, I'll let you know about that when the time gets closer. It'll involve more of the recent things. I haven't started Laplace. I haven't started Fourier transform yet, but I will do that this Wednesday. So let's see. Let me review what the problem is here. I'm going to stick with a square drum today. Before break, I did a rectangular drum. And to make life easier, I'm going to make my square drum have side pi. So this is the x direction, the y direction. And think of a membrane here stretched over a square drum head, square drum frame. Okay. The problem is d2u dt squared. If it was a heat equation, it'd be du dt. But a wave equation, it's du dt squared equals c squared times the Laplacian of u in the space variables x and y. Okay, and we would have that u of xy is pinned down on the drum frame, so that means u of xy equals 0 on the frame. Okay, so that's the problem. Today I'm going to take c equal to 1 just so I have less to write. And then let's see, if this is a drum, you got to whack it with a stick. And whacking with a stick would displace the drum head, so that have a displacement at time 0, and also it would give it an initial velocity. So to make this problem reasonable, you need u of x, let's see, there's a t variable. U of xyt is always 0 on the frame. And we would have an initial condition, u of xy at time 0, let's say it's some shape. You could pluck a drum head if you wanted to. And then also, if you whacked it with a stick, you'd have an initial velocity. So du dt xy at time 0 would also be some profile. So that's the problem. And last time I went through the classic separation of variables method and found a solution. U of x, y, t. We got a double Fourier series. The summation is n and m. Both go from 1 to infinity. So that's a double sum.
This might be an odd question, Professor, but assuming you hit it with a drumstick, time zero, there's been no chance for the surface to gain momentum because the impact.
Right, so that's you're thinking of a delta function. Right, so if you wanted to think of putting something in motion, you whack it with a drumstick and it would make a dent, and it would also make an initial velocity profile.
It wouldn't have.
Then when you let go of that, that's when it starts.
Okay.
That's when you take time equals zero, is when the drumstick no longer has contact with the drum. And if you want to idealize that thing, it's basically the definition of a delta function. It's a unit impulse of energy in a very short interval of time. And the delta function, you take that limit of time to go to zero. So it would be an instantaneous application of momentum. So that's how you come up with the delta function. It's like the ideal drumstick. Whack. Okay, so we had coefficients here. ANM. Let's see. Here's how I wrote it last time. No cosine. Sine NX, sine MY. And then we had ANM cosine. I'm going to tell you what these omega NMs are. They're frequencies. Those are the overtone frequencies of the drum. Okay, it wasn't hard to come up with this. Okay. And now if you look at, let's see, what are the omega n's? Where the omega n's are the frequencies of the overtones. And the funny thing about a square drum is that those frequencies do not make music. They're square roots of integers. And so those are all wacky, irrational things, and it's not a beautiful sound at all. It sounds like fire alarm kind of noise, or maybe worse. The pitch of the drum is the lowest frequency, which would be square root of 2. And all the rest would be higher overtones, and the coefficients would be smaller, so you wouldn't hear those as much.
What did you call the omegas again?
Frequencies. Okay, I'm going to show you what those look like. So let's see. I came up with that. Those all satisfy the boundary conditions. They satisfy the wave equation. And the last thing I have to worry about is satisfying the initial conditions. So the last thing is I need u of xy at time 0. That would make the sine term on this far out sine term that be 0. And this cosine term here would be 1. And so this is a double Fourier series. The sum as nm goes from 1 to infinity of ANM, a double Fourier sine series, sine my. Okay, and when I differentiate it and set t equal to 0, so this is going to be partial dt xy at 0. And that's going to be a sum as nm goes to 1 to infinity. When I differentiate that sine omega nmt, and omega nm comes out. And it becomes a cosine. And a cosine, of course, at 0 is 1. And the cosine term, when I differentiate, becomes sine, which is 0. So, when you think about it, I get omega nm bnm. These are double Fourier sine series. And in fact, it's going to determine those coefficients. This top one determines the a's, and the bottom one determines the b's. And this one's going to get the b's. Okay, so I want to explain. Yeah, question?
Should there be an M right next to the Y?
Yeah, definitely. That's better. Okay, thanks. These are double sines Fourier sine series. Let me show you how they work. So let's see. We need that top one to be summation. I'm going to write it like this. Sum as n goes from 1 to infinity. Sum as m goes from 1 to infinity. A n m. I'll put the sine nx. Let's say I'm going to pull out the sine nx. I'll put a sine. What do I want to do? I'll put the sine my here. First I'll sum over the m's, and then I'll sum over the n's. And I want that to add up to f of xy. Okay, that's a double sum, and I just decided to sum m inside first and then sum the n's. And if you look at that, you say, aha, if I hold y constant, that's a regular old Fourier sine series. So this is the Fourier cosine. Fourier sine. This is the Fourier sine coefficient, sine series coefficient for f of x variable holding y fixed. Okay, we know a formula for that thing. Okay, so we see that this sum as m goes from 1 to infinity, a n m sine my, that's the Fourier sine coefficient, which is 2 over pi, integral from 0 to pi of, let's see, f of y is being held fixed. Okay. And now if you stare at that for a second, you realize the thing on the left now is a Fourier sine series in y. And the function on the right is a function of y. So this thing right here is a function of y. And you know, if f is a twice differentiable, continuously differentiable function, this is a nice function of y. And so we can deduce that these Fourier series converge nicely to what we think they're going to converge to. All right. And so now we see that ANM is the Fourier sine coefficient for that f of y. So ANM is going to be a 2 over pi, integral from 0 to pi, f of y times sine my dy. And so finally we're going to come up with a formula, ANM. I'll put that f of y, what it is, in there. So I'll get a 2 over pi, integral from 0 to pi, integral from 0 to pi, f of x, y, sine nx, dx, dy. And by Fubini's, oh, there's another 2 over pi. And this is going to be equal to, Fubini says it doesn't matter what order you integrate in these double integrals. We're going to get integral 4 over pi squared, integral from 0 to pi, integral from 0 to pi, f of x, y, sine nx, sine my dx dy, an iterated integral. Okay, I should put that in a box maybe. Can somebody close that door, please? It's f of y is this thing, and I just replaced capital F of y with that integral that it defines it. Right, times sine my. This has a sine nx inside it. And I changed the order of integration, so just to, because I like dx dy better than dy dx.
So it also should be a sine my the first the second one.
A sine my. Oh, yeah, where did I skip it? Okay. Yes, you're right. Right here is where this thing should have come down and be right here. So that's a sine my dy. Okay, thanks for catching that. And similarly, when you do the same thing for b, similarly, let's see, there's going to be some omega n's in it. So we would get bnm equals 1 over omega 4 over pi squared. This, you know, these big things in the denominator make it converge even faster. So getting the omega n here, omega n, that's a big thing in the denominator. That makes these coefficients small. It makes everything converge even faster. Okay, so this is one approach to double Fourier series. You just do them in each variable separately, and everything works out great. And it's fun to play around in Maple and show that these things converge rapidly. So that determines the coefficients, and that's how you do it. An alternate way of doing the whole thing, so alternatively, sine nx, sine my are orthogonal. Meaning, let's call this phi n. Let's call this phi sub nm. And being orthogonal would mean that phi sub nm paired with phi sub kl that would be an integral over the square. Phi nm xy phi kl xy dx dy, that's going to be equal to 0 most of the time if nm is unequal to kl, and it's going to be equal to something, probably pi squared over 4, something like that. Not 0. You could calculate it easy enough. Let's see, what the heck would it be? I don't care. Unequal to 0 when nm equals kl. And so you could do Fourier series from scratch based on that observation. You know, you have Bessel's inequality, et cetera, et cetera. It all works exactly the same. Okay. But why the heck do it when we already have it all figured out and can just do it in each variable separately? Questions about that? Well, now for some fun facts. about drums. Those frequencies are ugly. So Nm equal the square root of n squared plus m squared are discordant overtones. So square drums kind of make a clank noise rather than a beautiful sound. You can hear the basic pitch if the fundamental is the loudest. That'll give you a pitch. But the rest of the stuff sounds like noise. Of course, the coefficients are small, so maybe the noise isn't so bad. Discordant overtones. And if you think about it, another weird thing is that another strange thing. A string, the frequencies were omega n equals n. Those are all 2 pi periodic. So cosine nt is 2 pi periodic. So when I plucked a string, it had a pluck shape. And if I waited long enough, it would have that pluck shape again. Remember? So, so those things are 2 pi periodic. A square drum these things are all weird irrational multiples of each other, square roots of something or other. They don't have a common period. So omega nm don't have a common period. So when you pluck a string, the shape, let me tell you what the string does. Don't have a common period. So a string, let's do a string. Remember when I made a little blip in the middle here? That's like whacking it with a drumstick, maybe. And then those would shrink, and I get, let's see, it'd be half the size going that way, and half the size going that way. There'd be a funny rabbit ear thing when they split up and go their separate ways. But they head off toward the edges. When they hit the edge, pinned down part, they reflect and come back. And then when they get to the middle, they would make a perfect repeat upside down. Then they'd go through each other and go the other way, reflect again, and come back and repeat the red thing. So that red picture gets repeated. So that's an interesting thing about the one-dimensional wave equation, that all those overtones are 2 pi periodic. So the thing is going to repeat. Okay, so the initial shape gets repeated. That doesn't happen with a square drum. So if I made a little TP pluck shape, let go, it would just go blonkers and never come back to that exact same shape again. Okay, that's a difference between a one-dimensional wave equation and a two-dimensional wave equation. Let's say this drum didn't have, this is an infinite string. Okay, I make a blip. then the blip would split into two that were half the size and go away and never come back. Interesting thing, if you're standing where that blip was, the waves go away and never come back. So it's totally calm there. That's way different than happens in a two-dimensional. If you ever drop a pebble in a pond, you'll notice that it creates rings that emanate from the center. The first ring is the big one, and then there's these smaller rings that eventually decay to almost nothing. But they never decay to zero. Okay, so yes.
Does that happen in infinite ponds?
Right. Well, you know, the energy dissipates. The waves get smaller and smaller as they go away. So it's not like these don't decay. But in a pond, those waves would spread out and the energy would spread out and it would dissipate. Question?
So essentially, the amplitude of each of the sun waves, it grows arbitrarily close to like the measure zero concept? Or?
The amplitude of the inner loop ones get smaller and smaller pretty fast. If you ever drop a pebble in a lake that looks like a mirror, the rings spread out, but eventually you don't see it much in the way of disturbance in the middle anymore. But that's Huygens' principle in famous. I know how to spell Huygens. Waves go away. Waves in R1, R3, R5. R3 makes sense. Now, if you shine a flashlight, that's a wave in R3. The light wave satisfies a wave equation, electromagnetic waves, and your flashlight beam goes away. You don't see any more light. It's gone. R5, etc. There's peace and quiet. The waves leave. They go away and leave space empty. Leave space in peace. And in R2, R4, and R6, etc., they don't. Okay. And by wave, I mean like a little delta function blip. That delta function blip would create waves that travel away and leave the space where the initial thing was in peace. That's pretty fascinating. And in the two-dimensional drum problem, the shape never repeats. It'd be all jumbled up, and you wouldn't see it repeat. I thought I'd show you a maple demo what those things look like. Questions about the math before I do the maple demo? So let's see. I'm gonna use Animate 3D, which is one of the commands you load when you type with plots. You'll see it there somewhere. Animate 3D is the second one. That loads that command. If you don't want to see that, put a colon instead of a semicolon. Now, here's one of those basic solutions. Sine nx, I took n to be 2. Sine my, I took m to be 2. Times the cosine is the wiggling part. I didn't put a frequency in there. That's where the square root of 2 squared plus 2 squared would be. So it'd be the square root of 8 would actually go there. But I wanted to I want to make it repeat, so I made simple frequency there instead. Now I'm going to push return. So it Animate 3D. I have a function of 3 variables. I'm going to make the x go from 0 to pi, and the y go from 0 to pi. So that's my square drum. And then the t is the animation variable. So it's going to sample the t variable from 0 to 2 pi and graph it continuously as t varies. That's the plan. There it is. I'm going to click on this. I don't see the controls for the animation. To make them appear, you have to click on this. And now the controls clear. I want to do a pretty slow frames per second. I'll do 4 frames, how about 3 frames per second. And let's see, this would go through one cycle. I want the cycles to repeat. So I'm going to do a circular cycle. That's in the t variable. Let's see, do I like this view? I can drag it around. I kind of like. That's kind of pretty, isn't it? Okay, now I'm going to push play. So there's like these little cells. And notice there's some spots, if you do the crisscross at the axis there, in the middle of there, those points don't move. So those are called nodes. And they're pretty interesting to look at, especially in different shapes that aren't square. Okay, that's one of them. That's one of the modes of oscillation. And it would have the frequency of the square root of 8. Questions about that? Now let me go back. Let me stop it. There's the stop button like a VCR. Oh, how about sine 3x times sine 5y? That should be pretty wild. Push return. Kind of starting to look like an egg carton. And notice all those spots that, now there's like a grid of places that don't move. Those are the nodes. And let's see, what this would have 3 squared plus 5 squared. Oh, this would have a square root of 25 is 5. So that would have a nice integer repeating musical sound maybe. But there's enough that are irrational multiples of something, weird square roots, that wouldn't be pretty. If you push play here, pretty wild. Interesting, you can make it, let's say I have a square something, you can vibrate it at certain, get a little something that hums and touch it, and you can stimulate these modes of oscillation. If you simulate it with a frequency that matches that frequency, you'll get some pretty interesting things. And you can do that with things that aren't square, and then finding those nodes, they put metal filings on top or something, and the metal filings would pile up on the nodes where nothing moves, and make very interesting patterns. And as you change the frequency, you get wilder and crazier looking nodes. And some of those patterns are really beautiful to look at. And there's some major mathematical conjectures about how those lines behave. Even in convex shapes, there's some open questions about how those nodal lines behave. So there's some fun math to think about there. Questions about Maple or any requests? It's a pretty easy thing to make Maple do double integrals. Just iterate the integrals, and you could calculate Fourier coefficients pretty easily. I wish I had prepared more. Putting a few of those basic terms in a sum and letting them do their thing is a pretty interesting thing to look at. Just put 2 or 3 in there, and you get some pretty wild and crazy. It's like there's water sloshing around in a bathtub. You get these great big peaks that go away and slosh around. Okay. Well, the plan for after spring break is to start studying the Fourier transform. And before I do that, I thought I would say a few words about a classic thing you might have seen in the ODE class, namely the Laplace transform. It kind of gives you, if you've seen Laplace transform in an ODE class, I think Laplace was before Fourier. And Fourier was doing series more than transform. So let's see. The Fourier, the Laplace transform, it takes a function f of x, and it sends it to a new thing, a new function, capital F of s, which is the integral from 0 to infinity of f of x e to the sx dx. Oops, e to the minus sx. Okay, so for one function of x, it's going to spit out a new function, which is a function of the s variable. Okay. And it's useful. This is an integral from 0 to infinity. It's useful for studying initial value problems. ODEs. Initial value problems at x equals 0 for ODEs. And engineers love it because it turns ODEs into algebra problems. Okay. Turns certain ODEs. It turns linear ODEs with constant coefficients into algebra problems. Okay, that's why it's fun. Okay, so there's a... Let me tell you what the big facts about Laplace transform are. Big facts. It's linear. Let's write L of f of x is that function capital F of s. Is a linear operator. Okay, that's easy to check. You just put f and a g, put them inside that integral. Since the integral is linear, the Laplace transform is linear. Okay, that's a big fact. A bigger fact, maybe from the point of view of ODEs, if I take the Laplace transform of a derivative, it multiplies the f of s by s. You just write out that integral there and put an f prime in there. And if there's an f prime there, it's irresistible to do integration by parts. You do integration by parts, think about it a little bit, and you realize, aha, it multiplies my capital F by s when I do integration by parts. And actually, there's a pain in the neck here. Well, it's actually a good thing, because this is going to have to do with initial value problems. Minus f of 0 pops out there. And once you know that formula, you can do it twice. So if I know that formula, I can do it twice in a row. I would write it out for f double prime. And if you do it twice, an s squared pops out. S squared times f of s. Minus s times f of 0 minus f prime of 0. Okay. Well, if you want to use the Laplace transform, you'd hit a differential equation with it, use the rules about it, and notice that these things would multiply by powers of s. That's algebra, and it would all be times the capital F of s. Hopefully you can solve for capital F of s, if you know a lot about a lot of transforms, and then undo the Fourier transform, Laplace transform. 3, we can undo the Laplace transform. I've probably been saying Fourier by accident, but I mean Laplace. Of course, that's the hard part. So the philosophical fact is, if the Laplace transform of one function, f1, equals the Laplace transform of another function, you only need to know it for big S. For all S bigger than some m, comma, then f1 and f2 are the same function. Of course, there'd be some conditions to have. You'd need differentiability, etc., for that to be able to show such a thing. Let's see, these functions are only for future time, so they would be the same function on 0 to infinity, the positive time variable. And so consequently, the inverse Laplace transform makes sense. We're going to have an inverse Fourier transform in a similar manner. L inverse makes sense. So the plan is, to show you the utility of this thing, plan Laplace transform of a linear ODE equal an algebraic equation in the f, in the s variable. So the plan is you take the Laplace transform of the ODE, you get an algebra equation, you solve for f, and then the solution would be the inverse Fourier transform. Laplace transform, geez. So that would be the inverse Laplace transform of f of s. Okay. A simple example. It's so simple you'll think maybe this is dumb. Let's take like y double prime plus 5y prime plus 6y equal e to the minus 4t. This would be a typical kind of problem, spring mass problem. So this would be a spring mass of k. The k here would be 5. The mass would be 1. No, the k wouldn't be 5. The k would be 6. The mass would be equal to 1. Mass times acceleration, so the m would go here. And then I'd put the minus 6y on the other side. That'd be Hooke's law with k equals 6. And the 5y prime is the, when I put it on the other side, it'd be minus 5y prime. That would be the friction term. So this would be friction term. Not the k, let's call it a c. So if you could take this either in a physics class or a mechanics class. I'm sure everybody's taken it someplace. Right, so if I was going to write the Newton's laws of motion here, I would have m y double prime equals the net force on this thing. I'd have the minus 6y would be the Hooke's law. minus 5y prime would be the force due to friction, which is in the opposite direction from the direction of motion. And then this other thing would be the net external force. Okay, so this would be Hooke's. That's the force from the spring. This is friction. And this is the external. So that's how you get an ODE from Newton's law, third law. Anyway, I'm going to hit that ODE with a Laplace transform. So I have Ly double prime plus 5y prime plus 6y. Of course, that would be the Laplace transform of e to the minus 4t. And then I would use the basic rules of Laplace transform. This would be s squared times the Laplace transform of y, and then we have some initial things here, minus s times little y at 0 minus y prime at 0. That's the Laplace transform of the second derivative. Then the Laplace transform of the first derivative would be s times capital Y of s minus y at 0 plus 6 times the Laplace transform of little y. It's 6 times capital Y. I'm using the linearity. And then the Laplace transform of e to the minus 4t is 1 over s plus 4. Which you can just calculate. It's an easy integral to calculate. Notice I've got a y to the s there, and the funny thing, the thing that's in front of y is going to be the characteristic polynomial of that of the ODE. And so when I can put all that other junk on the other side, why don't I give myself some initial conditions? I want to solve an initial value problem. I can write, let's assume I have, I won't do it yet. Anyway, I have to put all this junk on the other side. I'll get s times y at 0 plus y prime at 0 plus 5 times y at 0 plus s 1 over s plus 4. Oh, good, I'm running out of time. You can plug in the initial conditions. That'll put numbers there. Solve for capital Y. And then, the last step, you'll get some simple functions on the right. They're going to look like simple rational functions. That one even factors. And you can do you can do partial fractions and break them down into very simple terms. Let's see, let's take initial conditions to be 0. Just to make my life easier here. Let's take y of 0 equals 0, y prime of 0 equals 0. Then when I solve for, let's see, this is, what is it? S plus 2 times s plus 3. When I solve for that, I get y of s equals 1 over s plus 2 times s plus 3 times s plus 4. And then I would do partial fractions. Partial fractions. That would give me an a over s plus 2 plus b over s plus 3 plus c over s plus 4. And now I'm going to undo the Laplace transform. I'll get y of x equals a times e to the minus 2x plus b times e to the minus 3x plus c times e to the minus 4x. Should be t's.